I'm Saritha Kumari, Assistant Professor, EEE Department, Institute of Aeronautical Engineering College, Dundigal, Hyderabad. Under the course Performance of Transmission Lines and Cables, today the topic is relation between voltage and current wave in transmission lines. So, mapped to course outcome 4. So, we know that in transmission lines, basically in my previous lecture, we have started this transients in transmission lines. So in transmission lines, there is the traveling wave is nothing but a voltage wave or current wave travels along the length of the line at a speed of velocity of light under the transient condition. Okay, so now we're going to look at the relation between this voltage and current wave present in the transmission line, and also there are one or two small definitions related to this traveling wave, traveling voltage or current wave. So here's the point is the voltage. Consider a voltage and current wave travels a distance x meters in time small t. Consider the voltage and current wave travels a distance x meters, small x meters in time t. Then the inductance and capacitance of the line up to this distance small x will be Lx and Cx. L into x, okay, small x, and capacitance is C into x. Now, if we consider distance dx, the time is automatically dt, because in the beginning we mentioned wave travels a distance x meters in time t, then in time dt the corresponding distance will be dt. Now the line is assumed to be lossless. So we are mentioned that consider the line is lossless line. Okay, the losses are 0. That is resistance of the line is 0, conductance accordingly conductance J also 0. Then whatever the value of voltage and current at the beginning, the same will be at any time. Okay, the values of voltage and current, that means voltage wave and current wave at the beginning, the same is available at any time. Okay, so at any time t. This means that the magnitude of voltage and current wave at time t will be V and I respectively. So if we say at a particular time small t, the voltage and magnitude of voltage and current waves are V and capital I. So let us say that there are the values of voltage and current given to the transmission line. Now write the charge Q and the flux, magnetic flux. Consider, okay, the stored charge. Okay, the stored charge in the line is given by, because from the relation we know that, okay, C is equal to Q by V. The charge, if we write charge, stored charge, that is given as Q is equal to voltage into, okay, we are interested in a distance, at a distance x meters. So that's why it becomes, capacitance becomes C into x. So the charge is given by voltage V into C into x. Okay. Now similarly the inductance. Okay. Similarly, due to the inductance, the flux. Okay, this is a charge. Okay, value written from the expression of capacitance. Similarly, the flux. How can we write flux? We know that from the inductance definition, that is given by flux linkages by current. If we say that flux linkages number of turns, let us say 1, then it becomes pi by flux by I. Okay. Initially, definition of inductance is flux linkages by current. If we that is, what is the flux linkages? number of turns into flux. Okay. Now if we say the number of turns 1, then what is the inductance? Pi by I, flux by current. So from this, what is a flux? So the flux is written as in terms of L, inductance, current I into, okay, distance x meter. So L into x. Okay. Now from the definition of current, we know that current I is equal to dq by dt. Substitute for q. Okay, we know that what is q. So q is from the above, v, c, x. So v and c are constant. Okay, if we say write them out, then it becomes dx by dt. So we know that dx by dt is nothing but rate of change of distance is nothing but velocity of the traveling wave. So let us say that small v. Okay, dx by dt is the small v. Now therefore finally what is I? C, capacitance into voltage into small v. What is v? Small v, velocity of traveling wave. Say that equation 1. Now write down the voltage. Okay, so from the basic definition, basic knowledge. Okay, previously we know that current is nothing but dq by dt. Okay, in terms of charge, considered current definition. Similarly, next, the same manner, consider the voltage. Basic definition, we have expression for voltage in terms of flux. Okay, d pi by dt, rate of change of magnetic flux linkages. So if we substitute from the above, okay, so IL dx by dt. Okay, substituted for pi. Now again dx by dt is nothing but velocity of traveling wave. Say that equation number 2. Okay, voltage V is equal to IL velocity. Say that equation number 2. Now, okay, so previously I is equal to CV small v, that is equation 1. Now voltage V is equal to IL small v, equation number 2. Now we want to write the relation between this voltage and current. Okay, so that is what? So dividing equation 1 by 1 and 2. So that becomes V by I. Okay, V by I, that is given by IL by CV. Okay, small v, numerator and denominator gets cancelled. That becomes IL by CV. So write down this V and I, this left side. This becomes V by I whole square. The right side L by C. So finally, what is the relation between voltage and current? Square root of L by C. So that is in a transmission line, the relation between voltage and current wave. Okay, so this is a relation. Now, from the same equation 1 and equation 2, multiply equations 1 and 2, what we will get? Capital V into capital I is equal to, okay, CV into small v into Li into small v. So on left side, on right side, this what will be, we will see that okay, Vi is equal to CV small v Li small v, right? So okay, so left side, right side, we get cancel capital V and capital I. So what it is? Okay, C into L into V square. So from this, what we can write? Velocity, okay, square is equal to 1 by CL. So V square is equal to, that means C small v is equal to, so that is what? Equation, okay, small v is equal to square root of 1 by LC. Say that equation number 3. Equation number 3. So already we know this relation we come across in my previous lecture. The above expression is the velocity of traveling wave. L and C are inductance and capacitance of the line. if we substitute here those L expression, C expression, okay, so we'll know, okay, we'll know already that we'll get a value which is a constant value, okay, velocity of the traveling wave. That will see, let's see, that is a value. So for the overhead line, the value, the expressions of L and C, okay, L is given by 2 into 10 power minus 7 log of d by r dash, okay, this is L, and this C expression is 2 pi epsilon by, okay, log of d by r, okay, this is Henry's per meter, this is, okay, farads, we know that. Now these are the standard expressions for inductance and capacitance of a transmission line. Now if we assume, okay, this r dash in L expression, that is a self GMR, which is given by 0.7788 r, okay. So if we approximate it to r, okay, so what it is, log of d by r, okay, and in capacitance expression also we have log of d by r. So what it will, if we substitute here velocity expression, we know that 1 by square root of LC, right? So substituted here L expression, C expression. So this log of d by r, okay, this log of d by r gets cancelled, okay, substituted L and C expressions, okay. So this log of d by log base C, okay, d by r gets cancelled. We have only the remaining okay, value, constant value 4 pi epsilon into 10 power minus 7, okay, under root. Now we know that epsilon is the permittivity, okay, whose value is the constant value of epsilon substituted, okay, the epsilon value is 8 point, okay, of course it is the value, exact value is 8.854 into 10 power minus 12. So that is a epsilon value substituted, and finally the value of this velocity obtained as 3 into 10 power minus 8 meters per second. So we know that that is a velocity of the light. The value, this 3 into 10 power 8 is a value of the velocity of light. So that is what in the transmission line, the velocity of the traveling wave, that means that may be voltage wave or current wave, whose value is equal to velocity of the light. Okay, that is a point. Already this point we have I mean we came across previous, and one more point here is, here the speed of the traveling wave on the cable is less than that of transmission line. So this is a one okay, a specific point. We need to know the traveling wave, the speed of traveling wave in cables is less than that of the transmission line, okay, traveling wave velocity. Next, as I said, there are one or two small definitions here under traveling wave. We know that the traveling wave in the transmission line is nothing but voltage wave or current wave. Here this is in the form of a, most commonly it is in the form of a infinite rectangular or step wave, okay, a rectangular wave or step wave, and it is characterized by 4 specifications. Here see that the 4 specifications are, first one is crest. Of course in the figure we see a traveling wave, okay, a traveling wave. Here see that on the x-axis time is taken in microsecond and y-axis voltage is taken. So basically what is meant by crest, okay, what is meant by crest? Crest is nothing but maximum amplitude of the wave. Crest is nothing but, okay, maximum amplitude of the wave. So in this, okay, figure we see that what is the maximum value. So for this wave it is shown, okay, it is nothing but it is nothing but a step wave. So what is the maximum amplitude? If we see, this is a maximum amplitude. So this is called crest of the given shown traveling wave here. Okay, and it is expressed in kilovolts or kiloamperes depending. Okay, if it is a voltage, kilovolts. If it is current wave, that is kiloamperes. Okay, now front. Okay, so a simple front, in the name itself it is there. It is available before the crest. Okay, the front is available before the crest. Okay, it is a portion of the wave. It is a portion of the wave. Okay, available before the crest. Okay, that means this part. This part. So let us see here. So and it is expressed in time. Okay, this front is expressed in time, and it, from the beginning of the wave to the crest value. Okay, so this front is expressed in time from the beginning of the wave. So from the beginning of the wave to the crest value. So this is a crest value we know. Okay, so from the beginning of the wave to the crest value. Okay, this is a in the here it is shown T1. So T1 is a here front value. Okay, and one more thing, it is expressed in milliseconds or microseconds. Tail. So in the name itself it is there, but it is defined with respect to crest. It is available beyond the crest. Okay, tail is nothing but in simple, it is available beyond the crest. So portion beyond the crest, and see in detail how it is defined. It is a time, expressed in time, that taken from the beginning of the wave to the point where wave reduced to 50% of its crest value. Okay, it is taken from the beginning of the wave, to the point where wave reduced to 50%. Okay, from the beginning. So that means here, from the beginning to the point. Okay, this is a crest value, right? So it is taken from the beginning of the wave to the point where wave reduced to 50% after the crest. After the crest, where is that? Where is the point? This is reduced to 50%. This is the point. So to this point. So this is a tail, T2. Okay, and it is also mentioned in either milliseconds or microseconds. Now last one, polarity. So simple, polarity is nothing but polarity of the crest voltage value, okay, or current value. Polarity, it gives a polarity either positive or negative. So example, a positive value of 500 kilovolts crest, 1 microsecond front, 20 microsecond tail will be represented as 500 by plus 500 slash 1 slash 25. Okay, so a 500 kilovolts crest, a positive wave of 500 kilovolts crest, 1 microsecond front, 25 microsecond tail will be represented like this. Okay, plus 500 slash 1 slash 25. So that is how the polarity means for a traveling wave it is written. Okay, so so these are the specifications of the traveling wave, and these are the these points taken from the textbook. Okay, Selvagam Electrical Power System US Publications. Okay, so this is all for this lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.